we have the talk of Niall Emmart. He is the ZPrize winner, and now he'll talk about the achievements and how he got the prize. Thank you.
Thank you very much for the introduction. So this talk is about the prize category 1B. So it's an end-to-end proof of a zero-knowledge proof acceleration. There were many Z prizes, so this is just the last one that wrapped up recently. Okay, so the problem statement here is that you have to construct a plot-style zero-knowledge proof of a Merkle tree of height 2 to the 15. So it's like 2 to the 15 minus 1 nodes in the Merkle tree. And you have to run a batch of 4 of these proofs on a GPU, and you have to do that with the minimum energy. That's basically what the prize was for. The proof system is based on the ZK Garage framework, and the Merkle tree uses Poseidon hashing and VLS 1231 as its curve. We're given the circuit, and the only goal of this is you're not allowed to change the circuit, but basically just to optimize the running of the circuit to make it as fast as possible, or actually use as little energy as possible in the proof. So the circuit has a single custom gate, and I guess specifically it also can be optimized a little bit because the circuit doesn't use any lookups, which are part of the Plum proof system. Each of the Poseidon rounds requires 3 rows in the trace table, and each Merkle tree node requires 193 rows, which means the trace table size comes out to be 2 to the 22, and we end up with 21 columns. 5 of the columns are witness, and 16 columns are fixed. So this gives you some sense of the scale of the problem that we're trying to solve. Our submission is available here. It's in this GitHub link, and we achieved a time of 2.2 seconds to do a batch of 4 proofs. So when you look at the per proof time, it's 550 milliseconds for each proof, and to me this is a really significant result because Merkle trees are a super important data structure in blockchain proving. And doing it under a second means that essentially we've entered an era of real-time proving. So the problem calls for us to minimize energy consumption, but to me it's not exactly clear what's the best way to minimize energy consumption. So we just took a stab at it. We have to come up with an approach. So this is what we chose for the way we were going to do it. So if you think about GPUs can process a ton of data in a 300-watt package. So it seems like a reasonable choice that the GPUs are more energy efficient at doing big number arithmetic than CPUs. Right? We don't actually have solid evidence for that. We just sort of get it from the fact that you can do so many more computations per second. And so the obvious answer then is let's try and move as much of the work from the CPU over to the GPU. So that was step number 1. The second thing is that you really want to minimize your PCIe transfers, right? PCIe transfers are going to be expensive energy-wise, and doing it, so the less data you can transfer, the lower power you're going to end up with. The third thing is when you're on the GPU side, it's not even clear how you should optimize your kernels to make them the most energy efficient. So instead what we do is we just optimize them to say, let's just choose the fastest kernels. Right? So instead of really thinking about energy consumption, just think about speed for the kernels. And the final thing, which is sort of obvious, is that whenever possible, it makes sense to fuse kernels. Right? If you can fuse two kernels together, then you save a back and forth pass between memory, so it'll run faster and it'll use less energy because, like I said, moving data around takes the most amount of energy anyway. Okay, we tackled the project in 3 phases. So the first phase was that we optimized our proof system in the Rust code. Like I was saying, there are some arithmetic gates that are not used, and there are no lookups in the circuit. So you can remove all of that sort of stuff from the proof system and make the proof system more specific to the circuit that we actually have to optimize. Once we had finished that in the Rust code, the next step was to reverse engineer all of the math that's going on in that proof system and basically extract those math statements, and we rebuilt the same functionality in C from the ground up. Okay? And this required us to create some host libraries. We weren't particularly concerned with the performance of the C code. We just wanted to make sure that it was correctly reflected all of the steps that were going on in the Rust. And we could validate that by basically you kick off the Rust code with a specific input, and you kick off the C code with the same input, and you verify that the results were the same. Once we knew that we had the correct computation going on, the next step was we put it onto the GPU and onto an FPGA. And that's where most of the work was in the project. It was basically doing the GPU and the FPGA implementations. Okay. In terms of the GPU implementation, we basically did it ground up. So we didn't use any cub or we didn't use any thrust. And in terms of the primitives, you need MSM and NTT. So we took the fastest MSM submission from track 1A, which was the earlier ZPrize competition. And that was, Snarkify also had the fastest implementation for that. So we used that MSM. And we built a brand new NTT implementation for the project. The NTT is really well optimized. It's faster than any of the libraries that we've seen that also implement NTT. And I'll talk about that later in the slides. And then finally, I think it's important to note that the GPU card we have, that we were using, has 48 gigabytes of memory. So what that meant is that the entire proof can fit on the GPU, and you don't have to worry about any of these things where you have to stage the data across from the host to the GPU. It can just all reside on the GPU. And if they had chosen a different card for the competition, like let's say they had chosen a 4090, that might not have been the case. But we were lucky that there was enough memory there to fit the entire proof. Okay, so essentially our proof runs end-to-end on the GPU. And there's really only one piece of it that remains on the host, which is this transcript object. Let's talk about that. Really wish I had a pointer here. So the next 3 slides are going to go over the flow of a proof. So essentially the way to think about this slide is that this is showing time going down. We start out in the initialization phase, which is like a one-time thing that's done at setup. And during that phase, we copy the proof key from the host side over to the GPU side. So these arrows are showing the data that's actually being transferred over PCIe. And on this line, this is what's being computed on the host. And on this line, it's what's being computed on the GPU. So once the proof key is copied over and the GPU is set up, now we're ready to actually start working on proofs. The first thing that happens is round 0. We copy the Merkle tree over from the host to the GPU. Then we run the witness generation. Then we start round 1. Round 1 is the witness commitment. We do 5 INTTs and 4 MSMs. The 4 MSMs each give you back a BLS 12.381 point, which then needs to be committed to the transcript. And you'll notice here that we've jumped from round 1 to round 3. Traditionally in a plump proof, round 2 is related just to the lookup table. So we can, because we're not using lookups, we can eliminate that round completely. And here, when we start round 3, now we need some challenge values from the transcript object. These are a bunch of scalars. There's alpha, beta, gamma, those kind of things. Those go over the PCIe from the host to the GPU. And now we're ready to compute the Z polynomial. At the end of round 3, we send the commitments back. Similar for round 4A, challenges go over, compute quotient poly, commitments come back to the transcript object. But I should add, we have a bunch of time in this talk, so if anybody has any questions, feel free to interrupt in the middle of the talk and ask. I'm happy to take questions. Okay, and it's much the same thing on the third step. You run round 4D, challenges, linearization, evals come back, get included in the transcript. Round 5 is challenges, openings, commitments come back. And at the end of round 5, essentially everything that would have been computed on the host has now been computed on the GPU. And you have essentially the full proof object here at the end, and you just return that. Okay, so this table shows a breakdown of the rounds that were run. So the rounds are across the top. We have witness generation, and then rounds 1 through 5. And down at the bottom here, we have the total runtime for the round. So like witness generation is 2 milliseconds here. Round 1 is 112 milliseconds, 35, 317, 3, and 67. And in the middle part of this table, we show where that, basically a breakdown of the round time. So let's take an example of this round 4A. Here we have to do 6 MSMs, 6 coset INTTs, 6 coset entities, and 1 coset INTT. And that's where the times come from. And then in the very last column, we show the time for one operation. So for example, a coset NTT takes 14.45 milliseconds. So this gives you a nice picture of where the time gets spent during the proof. And I'm actually, this is a funny thing, we didn't synchronize our slides. There was another talk that Snarkify gave in the other room where we were saying that MSM and NTT are no longer the bottlenecks. Well, there's some caveats to that statement. In this proof, it turns out that MSM and NTT still are the bottlenecks. And the reason is because everything is being done on the GPU. Right? So because the whole proof fits on the GPU, we don't have any issues with waiting for data to copy over the PCIe bus. Any questions about so far? Yeah.
So is it possible to move the transcript object in the GPU?
Yeah, it would be. In fact, it's probably not that difficult to do it, but it just seems like it's more code and it's not very parallelizable, so you don't really get much benefit, I would say, between running it on the host, so why write more code?
Got it.
I have a question.
Yes, please.
So is there a relation between having 48 GBs of memory and MSM and ITTs being 24 minutes?
Yeah, no, that's exactly right. So because the proof fits on the GPU, then you're not waiting for stuff to be transferred back and forth. You don't have to schedule like some of the polynomials are going to be on the host and some of them are going to be on the GPU during this phase, and then we're going to copy other ones over before the next phase. It all just can live there. And so what that means is that then it's just sheer compute, and when it just comes down to sheer compute, then the MSMs and NTTs dominate again. Okay, the top 3 submissions for this prize, track 1B, were the Snarkify, the Voronov and Voronov, which came in at 770 milliseconds, and then Trapdoor, which came in at 3 seconds. So the first 2 place finishes are actually quite close. And so after the competition, we had a bunch of chats with them, and just to try and compare, like, how did they solve the problem versus how did we solve the problem. And it turns out they did pretty much exactly the same thing we did. So they ditched the Rust code and basically wrote the whole proof in C, and then accelerated that on the GPU. But then there was also the question of, like, where were the performance differences between our submission and theirs? And it turned out a lot of that came down to just having the fact that we had a better NTT implementation than they did. So what I want to do in the next couple of slides is just talk about our NTT implementation. So here's the relevant statistics on it. So our NTTs ran in 1.3 and 14.5 milliseconds versus 1.9 and 23. So we're about 50% faster on the NTTs. So the way our NTT works is we implemented something called the StockHam method. So StockHam is just another variation, a formulation, I guess, of the classical Cooley-Tukey. The big advantage of a StockHam NTT is that the data comes out in the correct order. Whereas on the Cooley-Tukey, the data comes out at the end of an NTT in sort of this bit reversed format, right? Like all the addresses that it writes to are bit reversed. So at the end of an NTT, that's done with Cooley-Tukey, you have to do a transpose operation. With StockHam, that transpose is eliminated. So what that means, instead of doing 4 passes, you can get the NTT in 3 passes. So it's essentially 33% faster than doing the Cooley-Tukey. The big disadvantage of StockHam is that it's an out-of-place algorithm, which means that you have to have 2 memory buffers, buffer 1 and buffer 2, and you basically ping-pong the data back and forth between the memory buffers. So what that means is that you need twice as much storage to run StockHam. And if you're doing giant entities, you probably don't have enough memory on the GPU card. But fortunately, these entities are small enough that we can have the 2 buffers and everything works out okay. Yeah, okay, I guess the last thing I want to mention here is that there are 2 sizes that are needed in the competition. You need to do a 2 to the 22 and a 2 to the 25. And both of those can be done with 3 memory passes using StockHam. And I wasn't sure if I wanted to include these next couple of slides, but given that I have a bunch of time in my talk, I think I'll go over them. So here's an example of basically doing a StockHam that's size 2 to the 22. So the basic idea is this. You lay out your samples in memory as sort of a 1D array. Yay. Thank you very much. Happiness is me with a pointer. Okay, so we lay out this data as 2 to the 22, and it's just in a 1D array. Okay, we can take this same data and we can interpret it as a matrix, right? We haven't done any copies on this data. We're just using a different indexing scheme to access the data. So you can think of this as a row major matrix. It's 512 by 8192. Okay, and again, this is completely free, right? You're not doing any work. You're just changing the indexing scheme, and that's used quite a bit in StockHam. Okay, so there are 3 passes that we have to do. In the first pass, basically we have these columns. Each one of these columns represents an NTT, right? And when we're loading up the data for this column, essentially the stride is 8192. So like this is going to be memory address 0, this is memory address 1, 2, 3, blah, blah, blah. This is 8191. And then down here, this is going to be memory address 8192. So basically, when you load this data up, you load it up with a stride of 8192. So here, what we're going to do is we're going to run all of these 8,000 NTTs. We're going to multiply them by twiddle factors, and then we store them out in this format. Okay, and here, like this 0 after we finish this NTT, it stores out there. Okay, and this goes all the way down to 8192, and then we're done with the first stage. Second stage is similar. You load in like this, you store out like this. There's going to be 16 of these blocks on the way out. Again, it's you do entities and twiddles, you just store them. And then, sorry, I'm skipping around here. I also want to point out that we're going from buffer 1, buffer 2, back to buffer 1 in this one. So like, again, we're ping-ponging between the 2 buffers, right? So then in the third stage, we go back from buffer 1 and then out to buffer 2. And this one we do 2 to the 18th, which is like 250,000 entities of size 16. So here they are, they're just listed like this all the way across, and you store them out like this. And by the time you finish that last step, you're done with the entities and everything is correctly ordered. Okay. Great. So almost done. I want to give a shout out to the team. There's Fabricio Maraca, he did the proof system optimization. There's Tony Wu, who's in the audience. Yay! Tony wrote a lot of the host code and worked on the FPGA implementation. And then there's me. I wrote host code, the host libraries, and I did the full GPU implementation. Okay, and this is probably the most important part of the talk. So I want to just give a couple of takeaways from this project. I think the first thing, and probably the big fish in the room, or big elephant, whatever the expression is, Rust and ArcWorks is actually a great environment for prototyping and researching proof systems, but it's a terrible environment for deploying proof systems, right? And it seems like a lot of people just, they just deploy Rust and ArcWorks for everything, as opposed to rethinking the problem. And the reason that they're so bad is that there's a lot of polymorphism in ArcWorks. For example, in ArcWorks, you can change the curve out by just changing the template parameters. Like you say, instead of using this curve, use this curve. Instead of using one commitment scheme, you can just switch it out to another commitment scheme. Or you can even change out full proof systems, right? All of that polymorphism comes at a runtime cost. Okay? So it's actually not very fast when you run it, because you say add A to B, well, it's got to go through all of these layers of polymorphism to actually get to the code where it actually adds A to B, right? So bottom line, Rust and ArcWorks are not that performant. Okay, so what's the takeaway? How do you really hit like super high real-time proving performance? Okay, and the answer is one, you have to have hardware acceleration, right? So there are three obvious choices. You either go with GPUs, FPGAs, or ASICs. Right? The second thing is that you really need to focus on having highly optimized primitives, right? You need a super fast MSM, you need a super fast NTT, and you need super fast polynomial operations, right? Because you're still going to be spending most of your time there. The third thing is that again, this is coming back to the ArcWorks. What you want to do is a ground-up re-implementation of the proof system, right? And you want to try and make this specialized for whatever your circuits that you're trying to prove are. So if you can eliminate something out of the proof system, there's no sense in wasting computing zeros. Right? So basically optimize it and make it as custom as possible. And then finally, I'll say, I don't think that Rust is a bad language itself, right? It's more the ArcWorks stuff that's built on top of it and the way people use Rust. But I still think that if you want to hit great performance, the best way to do it is write stuff in C. It makes you think about how the data is laid out. If you're going to put polymorphism in something, it's obvious that you're putting it there, and it takes code to actually implement polymorphism in C, right? So just doing everything in C gives you fast solutions, and then finally C is going to integrate better with your accelerators, right? So sorry to make a strong pitch for a language from the 1960s, but I think it's the right choice. Okay. And the final thing that I think is super duper important is that you want to make sure that you have enough memory on the accelerator for a full proof. Okay. And if you're doing something where you're like have a VM, maybe you should be thinking about making your proof size smaller. So you adjust your proof size so it just fits in the amount of memory you have on your accelerator. So it seems like a lot of proof systems, the proofs are just too big and they don't fit. But I think the idea is to make it so that your proof system can scale down and aggregate over more proofs. Right? I think that's the way to do it. But anyway, again, you make sure you have enough memory for a proof fits. Okay, and in my final slide, I want to talk a little bit about what are the choices, and obviously it's GPUs versus FPGAs and ASICs. So the big takeaway from, or another big takeaway from the ZPrize is that all of those sub-operations, the entities, the MSMs, the polynomial ops, they're all memory bound. Okay, they're not really compute bound very much, they're memory bound. Okay, so the implication is that even if you're going to go to an ASIC, you're going to have to build a really high performance memory subsystem, right? If you don't build a high performance memory subsystem, you're not going to be able to compete with GPUs, right? And when you go to ASICs and you know it's pretty hard to build like a great memory subsystem for an ASIC, and then there's also an expense, right? So people think ASICs are going to be really cheap, but the memory chips for high performance memory subsystems on ASICs are actually fairly expensive. You know, that might be half of the cost of a GPU card. So just switching to ASICs doesn't really solve the problem. You've got to switch to ASICs with a really great memory system, and that costs in time for development and in cost in the cards when you make them. Okay. The next thing is that it's way less work and to get a proof system up and running on the GPU than it is to build out an FPGA solution where the entire proof is running on the FPGA, or an ASIC where the entire proof is running on the ASIC. And then the final, I think, positive point about GPUs is that we're still in a situation where the proof systems are evolving, right? Like there's a lot of research going on in proof systems, and if you try and commit to an ASIC today, probably tomorrow there's going to be another proof system that your ASIC isn't going to work on, right? And you have to throw that out and do stuff. Okay, and then I would say, in terms of GPUs, there still are some cons, right? When we get to really, really high scale, maybe ASICs will make sense from a cost perspective, but we're not really there yet, where people are trying to do hundreds of thousands of cards or anything. We're still in a smaller scale. Okay, but when we hit vast scale, then ASICs might make some sense. And then finally, I would say that ASICs that are well designed are probably going to be more energy efficient than GPUs. But all of that said, from my eye, I think GPUs are the clear choice for the next couple of years, and I think that's the way Snarkify is betting. Woo. So, thank you. Any questions?
I had one question.
Yes.
So this was using Plonk and there were no lookups involved.
Right.
How does things change when you use log or so? And also, how do things change when you use improvements in the prices of things or use things? Does it actually change the metrics in terms of
No. Yeah.
Question,
Yeah.
and answer to the mic.
Yeah, okay, sorry. So I didn't catch all of your question, but I think a lot of it was like what happens if you change some of the underlying technologies, like you switch over to logup and things like that. I don't think it makes that much difference, right? So the main reason we remove things like the lookup tables out of the proof system is it eliminates computations that we weren't using. If we were using them, it might have added 1 or 2% to our runtime or something like that. So again, I don't think it makes any difference whether these things are whether you use those features. It's not going to kill you that you suddenly are starting to use tables. It's just if you can get rid of something, you may as well do that. Does that answer your question?
Yeah, and what about improvements in the fry? I think like there is stir, word, and base word, which includes the fry fry. Would that affect the entity amount of time that is spent in
I'm not sure. Can you ask me that question offline? Would that be okay? Sorry. Any other questions? Okay. Thank you very much.